Good evening, good morning, and good afternoon. Then Dr.Biplab Sarkar, Chief Medical Physicist, Apollo Clinic, several peer-reviewed publications in medical physics with many more academic and research contributions. Today, he will be talking about the role of artificial intelligence in radiotherapy. As you know, this campaign is to invoke awareness and to generate support for healthcare workers fighting the pandemic in the front line. As specialized scientists in healthcare, we also stand for life as we come across the challenging roads these days. So please feel free to use the question tab to type your questions.
I thank Oncores Foundation as well as Dr. Sanjeev Thomas for giving me an opportunity to speak in front of the August institution, August gathering. So that we are suffering from a typical condition of pandemic, but there is face-to-face interactions are limited, and we are also passing through a tough time. Okay, now artificial intelligence in the radiotherapy is my topic today. And what is artificial intelligence? The field of artificial intelligence was first conceived by a handful of scientists from the United States. The artificial intelligence is a conceptual category of computer software that designed to mimic or improve the human decision making. There are several kinds of broad categories of AI and all these things, which is called as rule-based expert system or machine learning system. The machine learning system is much more effective as well as popular system, and so those subdivisions we can see it in the due course of time or in the latter part of our conversation. Now the question is that the machine learning is a 60-year-old topic which is practiced 60 years, where the medicine is thousands year old practice, and the question is how we amalgamate, how we club these two subjects. That is the main concern of the present time. Now, where do you see an example of AI in our daily life? Now, if we want to type something in Google, or we are typing a mail in the Google. Now Google knows that this person usually send a quality assurance report often. So it gives an opportunity to me that it predict the quality assurance report before I type anything over there. So see, you can see that the quality, it is typed as the subject as a quality assurance report. So Google knows everything. How do Google knows everything? That is the question. The Google knows everything due to by the virtue of artificial intelligence. Now, this is the typical example where we face in the day-to-day life artificial intelligence. So we'll go to the deeper level. So from the artificial intelligence, we are going to the machine learning. Machine learning is the ability to learn without being explicitly programmed in some subject. Like we don't write a program for doing an integration using a Newton-Raphson method or whatever, but we are able to find able to do that integration program. So this is called as a machine learning. So we have to teach the machine how to understand this process. So in this regard, the deep learning is a subset of machine learning which will make the computation of multi-layer neural network feasible. Typically in the medical discipline, which requires a more accurate prognostic model like oncology, like pattern recognition system like radiology or pathology. So the machine learning can be effectively utilized for these subjects. We predict almost in another decade, almost 30% of the radiologist's job will vanish because it will not be required, because the machine learning based programs or AI based programs will give a better will offer a better reporting than a radiologist or a pathologist. So this subject like oncology, radiology, pathology will be definitely taken over by a portion of this subject will be taken over by the artificial intelligence. Now, whether it is for good or bad, probably it is for good. I'm not sure, but probably it is for good. But it is definitely going to happen, no matter whether it is good or bad. It is because industry and business require these changes. They require to incorporate the machine learning, or they require to incorporate the artificial intelligence. We should adapt. There are several instruments or several processes now is in place which could have been avoided, which is not of much use, but we have there have extensive use of these processes. Similarly, we should adapt the AI or ML based processes in the medicine where it works accurately than a human being. And it is for definitively a validated AI system. The AI system is much more efficient than a mid-level radiologist or a pathologist. An AI system is actually, if it is properly validated, it reduces the subjectivity in the subject or reporting. Now, what about surgery? Let us look at the most primitive or most basic medicinal discipline, surgery. Surgery is the highest achievable human skill. So even AI, artificial intelligence, even taking step into the surgeries also. Like it ensured the virtual reality devices are being used, and they direct the path. They direct the path of the automated needles, automated scissors, to go to the proper place without hampering, without rupturing the normal tissue or organs. So if AI can step into the surgery, then it will take over the other subjects as well. That is the prediction. Now coming to the oncology in general, what are the AI applications? There are several AI applications in oncology. One is the most prominent is machine learning algorithm developed in oncology. That we'll see it in the what are the machine learning algorithms we faced in oncology. And big data in oncology, which is also a big thing right now. AI application in cancer research, AI application in cancer care. Now, in this thing, in general oncology, the radiation oncology part, I have marked it in red. So pattern recognition, decision support, clinical research in the real world data, diagnosis, clinical decision support system, all things comes under the radiation oncology. When we talk about the oncology, we talk about the little bit of surgery, which is associated with radiation oncology, radiology part. Now, several publication which is coming into this method in this field, like machine learning approach for breast cancer prognostic prediction, or deep learning based delineation of head and neck organ. There are a lot of publications which indicate deep learning and machine learning in the oncology and the radiation oncology. Now, the important thing is that the future is big data. The big data is always big data is a big problem for us, and it will remain to grow as a bigger one in the future. In October 2020 last year, Seminaries in Radiation Oncology is a prestigious journal in radiation oncology, has dedicated a full issue in the big data in radiation oncology. There are 15 odd articles which is published in this issue. I should mention here, this journal is this journal is a only invited journal, means the editors invite some specialized people to put their papers in this journal. It is only the review articles published. Okay, so the big data, how big it is, if we consider that what is the how big the big data it is. Now, the biggest data usually is a human genome sequence, which is 100 GB order. Now, usually a normal genome sequence, which is not non-human genome sequence, which is nearly 1 GB data. So any data which is more than 1 GB as a movie, as a sequence data, as a text file is a big data here. Now, last week, early this week, I was going through a research protocol, which is regarding the cancer number of paper published in the Elsevier in cancer. So I come across a Excel sheet or a spreadsheet which is 172,000 rows. Now my collaborator told me that it is a mid-level data, it is not a big data. So the oncology data is also like that. It is not a very big data like human genome sequences, but it is a mid-level data which we handle in the oncology. Now, from this seminars in oncology, I taken 3 papers without getting into the detail because a lot of things to be stated in this half-an-hour talk. So I have just taken 3 articles: big data in oncology towards a goal of learning more from every patient, and use of big data for quality assurance in radiation therapy, and big data based administrative data outcome of toxicity evaluation. Okay, now what is the problem? The problem is we are unable to extract or store sufficient data from the patient or subject. That is the main problem of any medical discipline, because the medical discipline is a human discipline, which digitizing the data or getting the proper data is a very challenging thing. Now, getting into the paper 2 on this the previous screen, the big data for the quality assurance of radiotherapy. Now, what is the problem we face usually while modeling the while doing a model, that if every patient receive a dose which is lesser than a particular threshold, say for example in spinal cord all patients has received less than 45 days, so we don't have a knowledge that in the data how a higher dose would have impacted the patient. So without knowing the fact that higher dose, how the higher dose is affecting the whole process or whole system, so the model cannot recognize the importance of keeping the dose lower than the threshold dose in the range. Okay, so it is a big problem because we cannot, for our own experiment, we cannot deliver a higher dose to the patients. And if the sufficient data is not provided to the patient, to the model, the model's predictions is also wrong. So it is a two-way sword. Both the ways, it is a loss. You are creating a loss. Now, as we have discussed in the first place, that how AI and ML works, works through the ANN, artificial neural network. What is artificial neural network? I will come into a subsequent slides if the time permits. Okay, the basic theoretically, the basic philosophy, it is a AI and ML is a self-taught module which learn from the previous experience. If previous experience is correct, then learning algorithm is correct and efficient. Output is also correct. Otherwise, it is a disaster. If some of us who have worked more than 10 years in this field, the auto contouring modules which is sold to us or given to us 1 decade ago, we know how painful those auto contouring modules are. They cannot do anything almost. Okay, but now the situation has changed because there is a lot of evaluation, lot of modern techniques has been improved. The computers are fast, so we can have a better auto contouring. So you have to, the input, if it is proper, then only output can be proper. Now the question is, how do we answer any question? The information is stored in the memory in neuron and transmitted as an electrical signal. For example, if I'm being asked that whether there will be rain tomorrow, so I know there will be rain or there may not be rain. I can predict something and I can answer that. Similarly, the machine answer answered through a artificial or convolutional neural network. Conceptually, these things are more or less similar, but there are implementations are different. Mathematics is little bit different, and there are a lot of complications available. Complications are there, so on the implementation. Now, this is a typical slide which is being used for understanding the ML and CNN, machine learning and convolutional neural network. I am skipping this slide for the time being. If time permits, I'll come back to this slide. It is how the ML is identifying the, this is only philosophical concept, because detailing of a CNN is not possible in 2 slides. Okay, now I come straight to the AI in radiotherapy. Half of our time is over. So AI in radiotherapy, there are the radiotherapy is a 3-step process. First is diagnosis and decision making. The top layer, then the mid layer, treatment planning, physics check, plan approval, and the third layer, which is treatment delivery, treatment patient positioning, onboard imaging, treatment delivery, etc., etc. Now, the second layer can be very much taken over by the AI and machine learning. Okay, the first layer also partially can be used, partially can taken over by the AI and machine learning. A third layer also, there is some other than the patient positioning, there is a scope of AI to take over the process. Okay, now there are different systems for dose prediction. First one is deformation-based atlas method. Second one is fully connected neural network, and third one is the convolutional neural network. The third one, which is the bottom one is the most complex and most effective method until now to predict the dose for a particular patient in a AI-based system. Now, this is for the dose prediction. For contouring, it is the auto segmentation based on the convolutional neural network. Okay. Now, we'll go step by step. First, it comes to the machine learning on CT. Actually, there is not much machine learning or AI implication in the CT simulation, so-called CT simulation, but there is lot of effort has been made to radiological CT, which we are enjoying right now. Okay, so the AI implementation of AI in radiology is much higher than the radiotherapy. So we are enjoying the facility which we get through the radiology. Now, the effort has been made to reduce the dose to CT dose, which will enhance the image resolution, like low dose CT. We know this one. ML techniques are used to facilitate the CT reconstruction process. The CT reconstruction process is a very important process, which will actually which will use the prior information, the prior CT reconstruction to the raw from the raw image data. They will process with a prior iterative reconstruction using the previously stored data to get the proper reconstruction of the CT. So this process improved the quality of the CT scan very much. And then image to image machine learning approach aim to denoise. The noise will be reduced in the CT image after the reconstruction. So there are 2 steps. One is the CT reconstruction
I think Dr. Biplab,
efficiency reconstruction using the machine learning. Machine learning use the multimodal fusion. It is quite available in the images. So it will look for some similarity between the images and try to fuse it. Now, hello, is it there? Hello. Can you hear me?
It's here.
Hello. Hello.
Yes, we can hear you.
You can hear me?
Yes, you are audible now.
Like,
Yes, you are audible.
now, okay, thank you. The multimodal fusion, this aim to minimize the sum measures of similarity between the images. ML approach using a neural network trained as a binary classifier, means they use a patch-based system rather than the point by point matching. They use a patch-based system to identify the images and fuse it. This is actually a very effective method and much more than the conventional 3-point method or 5-point method or standard bone matching or bone interface matching method. So the multimodal fusion is quite good in majority of the planning system presently available in our commercial basis. Okay, so now the contouring. The contouring is the most vulnerable area, which is the largest source of uncertainty. Along with it is a very lengthy procedure. Subjective errors and inter-observer variability is also being observed for majority of the cases. So this can be reduced with the help of the AI-based system, machine learning-based system. The earliest attempt of auto contouring, which is actually edge-to-edge and region-based methods, which is actually a very primitive method and didn't improve the auto segmentation. It is actually, we know 10 years down the line, the auto segmentation tools are very primitive and we don't get anything out of it probably. Later, the ML incorporated systems, which has been introduced last few years down the line, and anatomical, it is incorporating the anatomical location or expected size of variation of the organ into the process. So this will give another dimension to the auto contouring process. And if you see, for example, a bladder volume, which is for a prostate patient, which is something like 250 cc to 600 cc or 400 cc. So if you know it beforehand that this is my bladder, this could be my bladder volume, so it will be easier for the system to contour the auto contour the system. Similarly, the position of the prostate lies between the bladder and the rectum. So or cervix lies between the bladder and rectum in a axial image. So if the system knows the position of the organ, then it will be much more easier to identify and do the segmentation. But the problem is that this segmentation, auto segmentation, in highly depend on the atlas selection. If the atlas selection is not correct, then it will not work. Okay. Now, for example, if you consider a European atlas and apply to a Asian patient, then it might not work as well. Okay. Now, there are several CNN-based technique which is used for the auto contouring. I chosen a recent report from scientific report Nature, and they have done a supervised learning. This studies from Korea. They have done a supervised learning for the CNN system with 120 hepatocellular carcinoma patients. This is a quite good number to validate the system, but let us see what is the result they have achieved. They have compared the CNN technique, the conventional neural network technique with atlas-based technique and ground truth contouring, the present contouring of the day. Now they have given these images, so we can see that there are a lot of discrepancies. The images are they have the auto contouring have done something, atlas-based contouring have done something, but they are not as accurate as a human contours. They seriously need a modification. Now we observed the improvements in the CNN technique, but not sufficient for the clinical use by any chance. So it need a quite good amount of volume of modification. The problem with these contourings are that sometimes these contourings are so confusing, and the end user gets so biased about this contouring, they try to delete everything and do their by own. They love to hate these modules. Okay, so it cannot be biased. The end user cannot be biased for contouring because they have something in their mind before drawing. If it is biased, that might lead to a potential error. Okay, so this is another example which is published in Red Journal a few days down the line. So they have used the expert radiation oncologist contour, inter-observer variability also they have identified, and deep learning or auto segmentation based contour also they drawn. So they have you can see that there is a lot of so inter-observer variation is quite high here. So this is another problem. So what is the advantage of auto contouring? The auto contouring advantage is it reduces the total timing from half an hour to fraction of minutes. Actually, in 30 seconds, all auto contourings will be over if the modeling is proper. So it will help to reduce the inter-observer variation. Sometime, but again the problem is sometimes it is very confusing, potential source of error, and still this contour cannot the contours cannot be used directly for the treatment, and they need a heavy supervision. Okay, what is the problem? Why it is not that good? It is not good because the supervised or unsupervised learning is insufficient. That means the problem is propagation of human thoughts in terms of memory to a machine is insufficient. Either the computers are unsmart or we could not taught them well. So we could not able to propagate our information, our thoughts to the computers. That is the main problem which I realize. Okay, now coming to that as the last portion of our talk, which is treatment planning. So what do you do with the treatment planning? We go down to a image set our BB, then go to the contouring module, see which images, which contours are overlapping with my PTV. So I found the PTV and then create a NOS non-overlapping structure for that particular for those contours. Then we draw a sphere contour, then we put the beams, then we put the optimization parameters, optimize it, iterate it during the optimization, get a good dose distribution, then dose calculation, then we finally get a calculated dose. Okay, so this is the process. So how long it takes? It takes nearly 40 minutes for variant system, and Electra system it is take 1.5 hours. Okay, that is also for a mid-level person. So this process is done by thousands of people, fraction of a million times per day. Now this 40-minute process, at least 3 cycles are involved in this process. 3 40 minutes will be involved to complete a plan. This process is somewhat mechanical process, and it can be reduced to 3-4 minutes, because see, there is not much intelligence involved in this process. So it can be reduced significantly using AI and ML. That the process, the people are trying to reduce this process. Still now there is some work has been done. We get some results, but not fully right now. Okay. The partial human intervention is required only for the setting up the beam. So that is also almost set for all departments. All sites also, it is also set that beam angles, whatever beam angles. Say for example a prostate, what should be the beam angle? I know there will be 7 static beam or a full or a double full arc which is rotating twice in the same position. So we don't have much choice on the beam angle, because after years of practice in the radiation oncology, it is almost standardized. Okay, so what are the other factors? The other factors are overlap contour elimination, sphere contour drawing, basic optimization parameter, change of the dynamic change of the optimization parameter during optimization, dose calculation, primary plan evaluation. These factors, these 6 factors should be automatic and AI or ML based. That will reduce significantly the timing of the whole process. Okay, the only stiff human intervention is required for the plan or DPH evaluation. This cannot be done in a AI basis, because this need to understand from the human perspective and look into it deeply. Okay, so some work has been done, as I told, but still long way go to find the zenith where everything will be automatically done. Now, what is auto planning? Auto planning is the all auto planning approaches mimics the process of iterative evaluation and adjustment made by the experienced operator. So all the auto planning approaches try to mimic a experienced treatment planner. That's the way it does. Okay, so auto planning systems identify the region of interest, appropriately introduce the additional objectives and priorities within the traditional optimization process. So you incorporate this. That means it is dynamically change the optimization parameter during the course of optimization and find a good plan for you. The KBP method, so all KBP methods are based on the geometric and dosimetric parameters from the from the library plans. Okay, so this is the basic understanding of the KBP. We will get into the detail of the KBP methods, which are the available KBP methods. Now, there are 4 KBP methods available in the present condition. One is the predicting the feasible DVH, dose volume histogram. This is called as the OVH technique, overlap volume histogram technique, which is the most common approach because it is adapted by the Varian also. Okay, so we'll call it a Varian approach, OVH technique. Second one is the one or more specific dose matrix. Third one is the voxel level doses, and fourth one is the objective function weights. I have taken this information from a paper published last year in the medical physics. It is a very good review paper. One can go through it. Okay. What about other vendors? We talked about Varian. We cannot Varian biased. Okay. So what about the other vendors? The other vendors like Elekta Erasmus iCycle, which is actually existing but not commercially available in the market. Okay. So it is developed by one of our friends, Peter Voigt. So I got some information from him, but it is all commercial planning systems work in a similar fashion, OVH technique. So there is not much to say about it. Then the third one is the Pinnacle IQ, Plan IQ, which is also a typical OVH technique. OVH compared the special relation between the PTB and OAR with the new patient with those patients which is previously stored in the library. Okay, so I'll not go into the detail reading out all these things. So we'll just concentrate on the 1 and 3. Say method 2 is not that popular, although there are some publications can be found. Now, overlap volume histogram is the prediction of the mean dose to we use for the predicting the mean dose to some organs. Okay. But what is the problem with the OVH? OVH technique always subsequently gives an error of 20% error sometime or higher. So this method does not hold good well for the serial organ. OVH technique errors in the prediction is sometimes very high, and final DVH curve may not actually represent the predicted value. The last one is written by Antonio Faglietta, which is published in Radiation Oncology. Now, so you can see that the bandwidths are so high. So what we are predicting here? We are predicting nothing actually, but we are predicting something very primitive, I believe, because bandwidth cannot be so high. Okay, so application of OVH, they will show you only these 3: prostate, head and neck, lung. There are several papers on this. Prostate is the most favorite thing. Why? That will tell you. Where is the stereotaxic basis? Where is the CSI? Where is the nasopharynx case. Brain cases are too low. Why this is too low? Because this OVH technique cannot work properly for large number of serial organs. Okay, so they concentrate on the prostate, head and neck, lung. That's all. But they don't go for the people don't go for the brain and all these things. Okay. So what is the alternate method? What is for the serial method? So method, it is the method 3, voxel level doses. First, it is developed in the University of California, UCSD, and this is ANN assisted dose gradient prediction technique for VMAT based KBP. Okay, so they have done with a 3D modeling, and they predicted the dose in every step. With they collected the dose information from the PTB and OARs as a geometrical function, and then analyze the function, analyze it as a function of PTB distance from the PTB. So this is the typical way they have done it. What is there is another technique available which is called as the ensemble mapping technique, which is actually developed by so it is depends on the it picked up the most suitable library plan from the multi-level from the library by a ensemble mapping technique. It doesn't look much, it doesn't uses any much complex mathematics. It is just tumor laterality, OAR is challenged or unchallenged, dose and fractionation level, tumor volume, center to center distance, edge to edge distance. And if you all these things are satisfied, then they'll pick up the plan from the library and use it in the new patient. So this is our institutional contribution in AI and ML, which we started in 2014. We collected the data for 196 patients, and then we digitize it, route them through a proper methodology, and so you can see it in the corner, top corner, it is the IP plan, independent plan, and the bottom one, it is a KBP plan. It is a knowledge-based plan. There will not be any difference. It can be almost, there is no difference except the some low dose levels. It is almost same. So it is a picked up plan, knowledge-based plan. So it is both. There is some publication which is we got it in medical physics, and it is presented in ISTRO 38 conference as well. Okay, so OVH technique is the KBP technique. All KBP method, OVH technique, all KBP methods are rely on the similar underlying concept, that is relating patient anatomy to dose, library matching, etc., etc. So there is no difference between this fundamental principle of the OVH technique. The differential averaging, which is the OVH technique, is not good for serial organs with a low prediction, high error in bandwidth sometimes. Now, non-OVH techniques like Shashi et al., so they have used a ANN, which is a very complex technique for the end user to implement. The other technique, which is Sarkar et al., it is does not hold good for the parallel organs as usual, and the data requirement is too high. The data library is too high. The data library of 196 patients is required to get a proper plan. Okay, which is a quite big number. Okay, so what is the present status? In the present status, it is fairly primitive. The treatment decision making, like in chemotherapy, like IBM Watson, is inefficient process, as per my understanding concerned. Then LINAC QA and all these things are all LINAC QA all are physically done, which is also a negative thing. I believe they have to be ML based technique. Contouring planning, again substandard systems. Chart checking is manual. Reaction evaluation is manual. Radiation safety is out of question with the ML based technique. Then what it should be, at least 50% should be the decision making should be the AI based, and part order and all these things also should be AI based. Planning should be 90%, 50% AI based. Chart checking also should be incorporated. Okay, now I'll just play this video. The typical AI system we are getting in radiotherapy right now, but I'm hopeful that another one decade, the situation will not be like, I did not have to show this video after a few years. So I'll skip this one because we are running out of time. It is AI and ML. So in the conclusive part, I'll just summarize the thing. It should ease out the medical physics job, decrease the role of medical physics as a medical physicist, and increase its role as a quality manager. That is my prediction. And then why we require AI in the medicine? Because large population deprived of proper diagnosis and treatment only due to the manpower. Say, for example, modern countries like Western countries like NHS, there are 23,000 CT scan which is unreported every year due to the lack of manpower. These things can be handled very easily with the AI systems. Okay, there are so many systems which is available in the market, available in the every aspect of life, which is taking over by the AI ML. So we have to adopt it. Okay, so we have seen there is a lot of fear psychosis working among the especially among the radiologists, that they are continuously discussing about the losses of job, and every in RSNA 2018, every 3.7th talk was every 4th talk was on AI or machine learning or CNN. Okay, similarly AAPM also, there are a lot of talks in AAPM last year. AAPM also lot of talks in the machine learning and something like that. So actually after the industrial revolution, workers who lost the job due to the industrial revolution, they come back to the factories and try to break the machines. They thought that breaking the machine will get their job back, but breaking the machine will not get the job back to those people. It is not possible. So similar thing, we have to adopt the AI and ML at any cost. Otherwise, we will be taken. We'll take a back seat otherwise. Okay. So what is the enthusiasm? ISTO 38, there was a long meeting, 1 day, 2-day meeting completely on machine learning. AAPM is doing a 4-day, 4.5 day school on the machine learning. ASTRO is having a presidential meeting on the machine learning. So it is, we can understand how much important it is. So there actually this subject can give a lot of publication. So a lot of people will be interested to publish, so they can look into this subject. This is a very interesting subject to publish actually. We can see that it is quite enthusiastic that people are publishing a lot in the radiation oncology and artificial intelligence, which I believe things will get into proper level in another couple of years. So the problem is that to understand the human behavior, is it possible to understand the human behavior? I put this question to you. You can look into this article from Tejpal Gupta, which is quite interesting actually. So I'll not, this is a question, very hard question to answer. So now the final question, whether bread and butter, whether our jobs will be affected or not. The question is whether computers have reduced the job in the society or increased it. Computers have significantly increased the skilled job in the society. So the AI will do. That's what my prediction is. There will be some loss of job initially, but that will get saturated. Okay, so there are some adverse effect of AI. They tell it is AI, but it's okay. This adverse effect will be there in every system. So I end up my talk. So I sincerely thank Oncores Foundation and Sanjeev Thomas. I am not sure whether you people have been able to listen to me or not. I thank Dr. Arjunan Manikandan from Apollo Cancer Center, Apollo Proton Cancer Center, and my colleague Shubhra Singh Viswal for their help to prepare these slides. Thank you.
Thank you, Dr. Biplab, for your excellent presentation. And it was very excellent presentation. I am sorry there had been some communication problems in between when we were changed the bandwidth. And in your opinion, I would appreciate to know what would be the impact of AI for medical physicists? especially you think in India? What would be your outlook on that?
Okay, we need to adapt the AI system. We need to adapt the AI. Presently, we are just doing whatever we are getting from some companies and all these things. But we need to have some AI scientists to look into the system, because we have lot of data and there is nobody to analyze those data. That is the main problem. We have lot of data. We generate in India. We generate a lot of data, but there is not. We don't analyze those data. So conceptually the systems are very straightforward, but the only problem is the mathematical portion. There are a lot of people which is around who do the. See, I personally don't know much of computer programming and all these things, but I have a lot of people around me, but I collaborate with them. They are quite efficiently handle those situations. So we need to increase the collaboration to get our data in a right way to analyze the thing. There is a lot of opportunity for a medical physicist in India to work on AI. Okay, and it is not going to take out the job. That is for very sure. Only the thing is that people have to be up to the mark. So otherwise, you cannot save that.
So it will be new technology that will help physicists to do more efficient job. That is what you are trying.
Yeah. We have to accept it. That's all.
Yes.
There is no two ways that we cannot accept it.
How technology is changed. So we are going to have some more better technologies to improve the quality and what they say, the speed of our work, I would say.
Yeah, that's correct. That's correct. We have to adapt this technology. There is no two ways, no question, out of question. Means just avoiding AI is just out of question now. If somebody says that, then it's not going to work.
It's true. Thank you so much. And there are many interesting questions from the audience.
Okay.
The first question is, what is your thoughts on auto contouring the GTV or PTV volume if you want to use radiomics for adaptive planning?
Radionomics.
Okay.
See, that present things are very clear. Like the auto contouring means if you have a previously done auto contouring, if it is the adaptive plan, then you have to always counter check it with your previous contouring. Otherwise, your visible the auto contouring mainly fails in the uniform areas. Okay, if there is not much variation, then there will be a failing of the auto contouring. Now the issue is that a CT scan understand 10 to the power of 4 to 10 to the power of 5 cells, not less than that. Now we need to make them understand, make the CT scan understand that you do a auto contouring, GTB contouring with the auto contouring, but you go back and look into it very carefully, because your eyes are more efficient than the contouring tool right now, because the human eyes are something like 200 megapixel, which is better than any camera right now until right now. Okay, so human eyes are better. So you need to look into it in a deep way and to identify the contours and then do the modification as per the requirement. I don't know whether I could answer the things in a proper way or not. Or radionomics means I am not very sure what is the radio.
It was good. Thank you. Thank you for answering the question. And another question we have is, the same question, but explicitly the questioner wanted to know how accurate is in comparison to the manual segmentation contouring.
Sorry, see, whatever. Now the DICE index for majority of the contouring, majority of the AI-based system is quite good. But the only thing is that these contours cannot be blindly used. Okay, these have to be verified and verified by a senior radiation oncologist. One cannot use a AI-based contouring directly for any patient treatment. Okay, so that is the problem. But otherwise, it is quite good, because I showed that report from the scientific Korean study. There are 1 or 2 cases it is failing, but otherwise it is out of I think 20 cases they have done, which is quite good. 18 cases they are in a very good position. but still it have to be well verified with a radiation oncologist, and minor modifications need to be done.
Okay, thank you so much. And the next question is, any AI system or model need to be evaluated before deployment. So how to evaluate or validate the model? We have prepared the data and we have prepared with the domain knowledge.
It is very easy actually. You create a library and then pick up a plan from the library, pick up a patient from the library, and see that whether it can reproduce exactly same dose distribution or not. You need to do a end-to-end test for a AI system. Okay, without doing a end-to-end test, you cannot go to use it in a clinical form. Okay, so if you say you have a library from A to Z plans, A to Z patients. Now you choose a patient, say ith patient. You choose the ith patient and rerun it in a library again. You choose the ith patient as a new patient and rerun it in the library and see that what is the difference it is creating with old ith patient. Okay, in DVH, in contouring, in DICE index, in paddock index, everything. You evaluate all the things and see that if it is a satisfactory, then you can use it for the clinical use. Otherwise, you cannot use it.
Okay. And there are many questions, but I will be going through only a few selected questions. And
Okay.
Another one is, can you please explain about the AI in research, genomics or phenomics?
Oh, but this is a very big topic. You can contact me. We can sit together and discuss it, because AI and genomics is a very vast subject. It is half an hour or 20 minutes. I cannot make you understand genomics. I also don't understand fully, but I have one collaborator who is working in the Human Genome Project, in that US-based project. So we sometimes have a discussion on this. So we little bit understand the process, but it is a very complex process. It is a very complex process. Means there are a lot. Genomic process completely AI-based process. No human intervention is there actually. So nobody can manipulate. Nobody can get into it. Means so it is a fully computerized AI-based system.
Okay, thank you so much. And another interesting question is a few examples of auto planning in the markets. Could you please comment about some of the auto planning models which are available in the market?
See, there is one is available from the Varian, which is quite good for the prostate, lung, head and neck cases. And then there is a Plan IQ, which is also from the Philips, which is also good. And there is a new planning system has come, which is they use it for the proton. I don't know I forgot the name. There's some planning system. Research planning system. There is something research planning system. Research also having a very good auto contouring. Actually, research is the best one, I believe, among all these modules. But anyway, it's need to be validated. Means everything have its own demerits.
Okay. Thank you, Dr. Biplab. And there is one more very interesting long question. With the advent of AI, particularly how it revolutionized the way of thinking and its application in medical physics, then how should it adapt to these changes? Meaning, how do we prepare ourselves when time comes where AI systems will take over some manpower currently done by medical physicists? Do we need to be cautioned, or should we embrace them without hesitation? So I think the second part we have already discussed. Maybe the first part, how the medical physics community should be prepared.
See, medical physics as a whole, everybody is preparing. It is a radiologist is preparing, a surgeon is preparing. So medical physics also have to prepare in the same way. The main concern here is the data analysis part and learning the modern technique to analyze the data. If you can analyze the data, then your value will never go down. Okay. Now, see, the analysis part is the research. Say I do a lot of plan, I do a lot of QA. This is a very mechanical portion. It's a technician job. So it is not going to. It's not going to help anybody out. Okay. Now if we cannot analyze my QA result for 10 years or my planning result for 15 15 years or my outcome result for 20 years, then that is actually of no use. Means we do whatever it is a waste only. Okay, so the main concern is to get ready with the processes, ready with the mathematical processes to analyze the data. If you can analyze the data, it is all fine. Nobody can take you anything out there. Means you will be the quality manager. So medical physics will go and you will be the quality manager. That's all. Radiotherapy quality manager. Maybe RSO. Instead of RSO, you will be called as a quality manager. That's all. Your designation name will be changed. That's all. Nothing less, nothing more.
And but how the AI, how the regulation is going to adapt with this change? That will be another question.
The course regulation have to adapt, otherwise they will change the regulation. That's all. Yes. See, for example, I'll tell you one example. In United States, there was a problem with the stereotaxy prescription and SRS and SRT prescriptions. So the definition of SRS has been changed from 1 to 5 fractions so that the insurance coverage can be get. Okay, so if the regulations regulation do changes with the advancement of the things. Okay, so we are getting a machine which don't have a linear accelerator, which don't have a field light, and regulation accept that. A halcyon machine don't have a field light, or a Tomo machine don't have a field light, and regulation accept that. So if it is not harmful to the society, well, regulation will accept it. That's all.
Of course. So thank you, and we are running out of time, and so once again I thank you. And once again I thank you, and my apologies for the technical problems at the beginning of the webinar.
So
as you all know,
otherwise it was listenable.
Yeah, it was listenable to everyone, and it was very good. It was a very good presentation. And I'm sure all those who are attending this session will go back and start thinking how they are going to adapt the technology. Definitely, that's going to be one of the outcome of today's webinar. And as we know, this campaign has started for supporting the healthcare workers who are fighting the pandemic in the front line. And also now this has grown to all the major continents with more than 400, 500 registrants for each webinar. So my request to those who are participating in this webinar is, if you have a pandemic management protocol in your organization, please feel free to share with us so that we will be able to share those information to all those who are participating with us through our emails and through our social media groups. So that is some of the good thing we could do as a community of medical physicists that's coming together to support the humanity now. And now we are known as Medical Physics for Life, with a more direct application to the life, and trying to help more people from this seminars in terms of information, awareness, and other ways, whichever is possible. So I thank once again Dr.Biplab Sarkar for supporting this campaign, for volunteering this lecture by sharing your expert knowledge. And I thank all the participants for your active participation and for the questions. And I welcome you all for the future webinars. See you again. Thank you.
Thank you, Dr. Sanjeev Thomas and Oncores Foundation for giving me this opportunity. And thank you for listening to me, all the people. Okay, thank you. Bye.
Thank you. Thank you.